All right, so in the previous video, we talked about the definition of slice rank, and we also had a lemma about the slice rank of the hyper matrices, which are diagonal. And now we're going to show you how we can use this lemma to reprove the theorem on capset problem by Ellenberg and Guzik. So let me remind you what the theorem is. So the theorem is the following, right? So if you have a subset of f3 to the n without three-term arithmetic progressions, then the number of elements is bounded by this. And the previous proof wasn't symmetric with the three variables, so we're going to show you alternative proof proposed by Terence Tao. So what we are going to consider is the following function. So for a in f3 to the n, let f x y z to be 1 if their sum is 0 and 0 otherwise. Right? Yeah, this is for x, y, z in A. Now, what we observe is if x, y, z is a three-term arithmetic progression in f3 to the n, then what do you know? What we know is x plus z is twice y, right? But twice y is equal to minus y, so x plus y plus z is 0, right? So this means the fx plus y plus z. Okay, so this means if A has no three-term arithmetic progression, then f of x, y, g is going to be 1 if x is equal to y, that is equal to g, and 0 otherwise. And this is a perfect setting for the previous lemma on the slice rank, right? So look at this lemma, right? So if you have a function where non-zero values only occurs when all these coordinates are equal, then slice rank is equal to the number of non-zero entries. So this implies that the slice rank of f is equal to the size of A, right? Oh, by the way, when x and y and g are equal, then x plus y plus g is 3 times x, but since this field is f3 to the n, so 3 times something is 0 anyway. So now we just need a we're going to use this slice rank. Now here's a lemma, right? The slice rank of f is at most 3 times n, where n is the same as that, right? Where's n? Let me just copy. So a, b, c is non-negative and their sum is 0, oh no, n, and we are summing over a factorial, oops, b factorial, c factorial, and b plus twice c is at most 2n over 3. All right, so how do we prove that? Now let's look at this fxyg. You can think of it as a product of this, right? For each coordinate, if xi plus yi plus gi is 0, then we're multiplying 1, right? So 1 minus 0 is 1. And if it's non-zero, then we are multiplying 0. Because if this is plus minus 1, then 1 minus 1 is 0. So this is exactly the description of this function. This is the same function. All right? So you can write this as this polynomial. Now we're gonna expand it. The right hand side is a linear combination of monomials of the form, like what's the form? Like x1 i1, x2 i2, xn in, and y1 j1, y2 j2, yn jn, and g1 k1, g2 k2, gn kn, where these exponents these exponents are non-negative, and they actually at most 2, right? Because you can only have a square, and their sum is what? Is at most twice n, right? That's the degree of the polynomial. Now, so then what we know is the sum of IL, let's say, and sum of JL and sum of KL is at most twice n, right? So that means either sum of IL is less than or equal to 2n over 3, or sum of JL is less than or equal to 2n over 3, or sum of KL is less than or equal to 2n over 3 for each monomial, right? Because after you expand, for each monomial, there's some term, maybe some of the i's value, some of the I value is small, or some of j value is small, or some of the k value is small. Now we'll rearrange them, right? So for instance, among all monomials with the sum of IL is at most 2n over 3, we can rearrange and regroup these monomials as sum of f of alpha x. So x, the exponent of x vector, was I1 up to IN, right? And then G alpha YG, where alpha is some vector I1, I2, IN, with all these values are at most 2, and it's 0, and their sum is at most 2n over 3. And the number of choices of alpha is actually equal to n, right? Why? Because we gonna what is n? N is this thing. So that A is the number of times you choose 0, and B is the number of times you chose 1, and C is the number of times you chose 2. So B plus twice C is at most 2n/3, and that's it, right? So what do we get? So we can think, so thus fxyg is equal to, let's say, f alpha x g alpha yg plus, let's say, beta. Okay, is it a good notations? Fg f prime, no, let's not use prime. F, I need a name. Okay, f one. Okay, fg h f bar. No, so for when the exponent of, when the sum of the exponent of sum of the j value is at most 2n/3, you can decompose it like this, right? And when sum of the k value is small, then you can decompose like, okay, f gamma g and g gamma xy, and the number of times is each of them goes over n times. So this means that f can be written as 3n, sum of the at most 3n slices. Right? So the slice rank of f is at most 3n. So that's what we wanted to prove. All right, so this means, therefore, the size of A is at most 3n. Does that make sense? So that's the proof. And we already knew that this form, yeah, is a little of 2.756 to 10. All right, that's it.